Alright, this is Mr. Peterson with another screencast for AP Environmental Science. Today, we're getting into some specifics on air pollution. Some of the stuff we have to deal with regarding air pollution may just make you want to hold your breath, but that's not going to be a long-term, sustainable solution unless your plans for the future are very, very short. First up in your notes is the atmosphere, which is the layer of air that separates the Earth's crust from outer space. Although the atmosphere technically extends to an altitude of around 75 to 80 miles, most of the business that gets done in the atmosphere happens in the bottom 30 miles or so, and that's because the air is denser at lower altitudes. Here's a picture of what I mean. I see the atmosphere as this thick blanket of air that surrounds the Earth. The thing is, molecules of air are pulled down by gravity. That's what keeps the whole atmosphere around Earth. Look at the moon and the smaller planets. No atmosphere, because they're too small to have enough gravity to hold the atmosphere on. So, since gravity is pulling down on the air, it settles and is more dense at the bottom, because the molecules are tightly packed, while it's less dense at high altitudes because there's fewer molecules there. Now, atmospheric pressure works in a similar way, that it decreases as you increase your altitude, but for different reasons. Atmospheric pressure is the effect of the weight of all of the air over your head pushing down. So, as you go upwards, you have less air above you pushing down. So, the atmospheric pressure decreases. It pushes in all directions on you, and your body pushes back with its own internal pressure. So, you don't get crushed by it. If you don't believe me on the air pressure thing, it's okay. It's really hard to see. But here's how you can see it. Take a suction cup and stick it to a flat surface and try to pull it straight off without peeling it up from the edge. If the suction cup is big enough, it's nearly impossible. Why? Because when you press the suction cup against the surface, you pushed out all of the air under it. That means that air pressure is only pushing on the outside of the suction cup, so it's held to the surface you put it on. Try to pull it straight off, and you have to overcome the force of the air pushing on it. And that registers as a force of 14.7 pounds per square inch of surface. So, this little suction cup, if it has a radius of 1 inch, would have a surface area under the cup of 3.14 square inches. So 3.14 times 14.7, that works out to be about 46.2 pounds of pressure. So pulling the suction cup off would require as much force as picking up a 46-pound weight. And, for your own reference, the biggest plate on this bar tips the scales at 45 pounds. So, how do you get the suction cup off the window? If air pressure is so powerful, easy. You don't overcome the force at all. You pull on the little tab on the side, and even someone with puny muscles can overcome the force of air pressure acting on that and peel the suction cup off the side. So, air pressure is there, but it's hard to see. Now, the two layers of the atmosphere that we're concerned with are the troposphere and the stratosphere. The troposphere is a layer that extends from the surface of the Earth up to the level of about 5 to 11 miles. It ranges in size because it's thicker at the equator than it is at the poles. Most commercial jets that fly at 30 to 40,000 feet are towards the middle of the troposphere, but none fly above it because there's not enough oxygen in the air to support regular combustion, and the air isn't dense enough to provide lift for regular planes. The gases in the troposphere are what we breathe, and it's a mixture of 78% nitrogen, 21% oxygen, and the other 1% is made up of water vapor, carbon dioxide, and ozone. Several other gases that are present in very tiny amounts. And I would have memorized those percentages. Now, in the stratosphere, which ranges from the top of the troposphere out to about 30 miles, and it's made up of mostly nitrogen and oxygen. Again, but the density of the air is very low, so people refer to this as being thin air. If we took you up from here to the level of the stratosphere, you'd be gasping for breath, just sitting still, because each breath you take would contain far fewer molecules of oxygen. So, your body would respond by making you breathe faster just to keep up. Now, the stratosphere has one other important difference. It contains all of the ozone. Important fact. That's important for blocking ultraviolet radiation and keeping it from reaching the Earth. And that keeps us from having to wear sunscreen with the SPF of Avogadro's number. So, next up is air pollution. Air pollution occurs when there are substances in the air at high enough concentrations that result in harm to organisms, ecosystems, or man-made materials. This is a pretty extreme example from Beijing, which is currently suffering from some of the worst air pollution on the planet. This isn't fog. It's just air pollution. Just looking at this makes me want to go outside and breathe the clean air we have so very deeply. And let me add, I have been to Beijing, and let me add, it was pretty bad. The pollution was so bad I could stare at the sun in the middle of the day and it would not even bother my eyes. It was a constant haze, fog, or basically just pollution always over Beijing, and I wasn't there on really bad days like this. But it was constantly there, and they have a constant problem because of all the combustion and lack of regulation. There are two major sources of air pollution. The first one is point source. also known as stationary sources. Point sources are any source of pollution that are in a fixed place that you can essentially point to on a map because it can't move around. And therefore, power plants and industrial factories both qualify. If you can point right at it, it is point source pollution. And now, on the other hand, cars qualify as non-point source pollution, also known as mobile source. It's easy to point to a power plant and say, hey, it's causing air pollution, because you can see it. And the pollution is concentrated from one source. But cars make up a lot of air pollution we have today. But it's harder to see because they're more spread out and there's more of them. You can't just point at one. You have to point at thousands, and you don't have that many fingers. Next up, we've got primary pollutants. Those are harmful chemicals emitted directly into the air from the natural process and human activities. Secondary pollutants happen when primary pollutants react with each other in the air to form a new harmful chemical, like ground-level ozone. First up in the air pollutants is carbon monoxide. Carbon monoxide, or CO, is a colorless, odorless gas that is highly toxic. It forms when carbon-containing materials like wood, natural gas, and gasoline are burned without enough oxygen to fully support combustion. The danger of CO is that it binds extremely well with hemoglobin in the red blood cells. It's like chemical superglue, so that it reduces the ability of the blood to carry oxygen around. So even though you're technically breathing, oxygen isn't getting to where it needs to. The signs of CO poisoning are hard to pick up. And because of the early signs look and feel like you're just getting tired, it's an indoor air pollutant problem that some people die from every single year. Because they fall asleep and lose consciousness or just get confused, and then they die because of lack of oxygen. If you have a gas water heater or furnace or a fireplace that you use, I'd highly recommend picking up a CO detector. In fact, you need one. They look like smoke detectors, but they only go off if CO is detected, and most smoke detectors now have a CO detector built right in. Ours is right in the hallway. So, if there's ever a CO problem in my house, it will wake me up before the concentration gets high enough to cause damage. Now, I'm not going to go through each of these major pollutants in your notes because you're quite capable of reading the book to get the important details for each one. And at this point in the year, you should be quite efficient at it. So, let's move on. Well, before we do, here's a picture of what happens. Now, let's move on. Oh, wait. Here's another picture of some of these side effects. But let's move on. Oh, wait. Here's one more. It's a picture of the carbon monoxide alarm detector thing. But let's move on. All right, we are moved on this time. Sulfur dioxide. Sulfur dioxide is a gas that released into the air mostly from burning coal that contains sulfur. The problem with SO2 is that it combines with water in the air to form droplets of sulfuric acid and solid particles of sulfate that fall back to Earth, and it's called acid deposition. The liquid part of it is what we call acid rain. This is a problem because the acid can damage trees, crops, and even aquatic life in lakes, rivers, and streams. It can also damage buildings and statues over long periods of time. Battery acid is concentrated sulfuric acid, but the damage from very dilute amounts can be seen on this statue. Where the surface of the stone has been worn away by acid deposition. Normal rain is slightly acidic because of the carbon dioxide of the air that combines with the water, making it kind of carbonic acid. Now, acid rain isn't to the point where you're going to walk outside and melt your skin. This is going to be over time, over many different rains. This is not to occur over one acid rainfall. The last one I'm going to go over here is ozone, and that's O3. It's colorless, but not odorless. It has a very irritating smell and can cause you to cough. It can irritate your eyes and nose, and it's also highly reactive, so damages lots of man-made materials as well as plants. Ozone in the troposphere is bad, and it's not normally present outside of what we make in our air pollution. But ozone in the stratosphere is naturally produced, and it's needed in order to shield us from UV radiation. It's a shame we can't just take all the ozone from the ground level and ship it up to the stratosphere. Now, be sure to check back with the book for details on the other major pollutants that I'm skipping over here. Next up in your notes is smog. Smog has a term originally coined in the 1850s to describe a mixture of smoke and fog, but now it describes any mixture of chemical pollutants in the air. Industrial smog occurs when sulfur dioxide and sulfuric acid mix in the air along with a variety of suspended solids like dust, and the air takes on a grayish color. So sometimes it's called gray air smog. This picture doesn't have a filter applied to it. It's just brown air smog, or photochemical smog. It occurs when primary and secondary pollutants are influenced by UV radiation from the sun and converted to new pollutants. Brown air smog is caused mostly by outputs of nitrogen monoxide from cars, and when it When it is hit by the UV radiation, it converts into nitrogen dioxide, which has a brownish color. That's why photochemical smog gets worse on hot, sunny days in large cities, because the morning commute has loaded up the atmosphere with primary pollutants, and the increased amount of sunlight does the rest. Now that we're all depressed about how dirty this air can be, let's move on to ways that Earth cleans the air in order to keep it as a renewable resource. First up is gravity. Heavier particles settle to the earth. So, when the air is still, the larger particles of pollution will settle to the ground. That's great for cleaning the air, but it's bad if country A makes loads of air pollution, sends it high up in the atmosphere, and then it settles out of that country A and into country B, which is downwind. Now, how do you regulate an entire country's air pollution emissions? For example, the United States produces lots of air pollution problems like acid rain for Canada and the northeastern part of the United States, southeastern part of Canada. The second way the air is cleansed is through rain and snow. Raindrops falling through the air pick up pollutants and essentially wash them out of the air. Ocean spray actually does the same thing. Each wave washes out the air it crashes through, and although one wave may not be very big, multiply it by the entire ocean and you can see an effect. Wind is the fourth factor that cleans up air pollution. In the bottom picture, the factories in the city created air pollution, and the wind speed is slow, so the pollution lingers in the air. In the top picture, the wind speed is higher, and that's removed some of the air pollution and made the air cleaner. Now, that pollution has just moved somewhere else and become less concentrated as it mixed with fresh air, but they're just saying here you should know. Sometimes the solution to pollution is dilution. Simply spread it out over a large area, and it's not as significant, or natural processes can then work on it more efficiently than when it's all crowded together. Now, chemical reactions in the air can remove some pollutants as well. The gray arrows in this picture show air pollution entering the atmosphere, but the blue circle arrows are chemical reactions. As chemicals combine in the atmosphere and form new compounds, sometimes those compounds can fall back out of the air like sulfur dioxide does when it forms sulfuric acid and leaves the air in acid rain. Not that it's a good thing, but it does cleanse the air. Air pollution can be increased through 6 factors. First up, large buildings can slow wind speeds and hinder the removal of air pollution. Or hills and mountains can trap pollutants in valleys because the air flows over the top of the mountain and the leeward side of the mountain experiences slower wind speeds. It's really like the previous large building example, except the buildings are really big and we call them mountains. High temperatures are up for number 3 because they can promote chemical reactions that lead to smog and ozone production. And fourth, some plants like this sweet gum tree emit volatile organic compounds, or VOCs, that can play a role in smog production. Fifth is called the grasshopper effect. It occurs when air pollutants are carried from where they're created in the tropics and temperate zones all the way to the polar areas of the Earth, where wind patterns can tend to trap them and concentrate them, leading to high amounts of air and eventually soil and water pollution in very unpopulated parts of the Earth that are still crucially important for all humans on Earth. And last up is temperature inversion. Now, normally air temperature descends as you increase your altitude. There's even a conversion factor. The temperature will decrease an average of about 3 degrees Fahrenheit per 1,000 feet of elevation. That's why going up the Appalachian Mountains, which run in 35-foot range, can give you 10-degree cooler weather in the peak of summer. Temperature inversions can happen when weather patterns create a system where the air aloft is warmer than the air at the surface. So, forms of air pollution like this smoke will rise as long as they're warmer than the cool air around them at the surface. But when it hits the warmer layer of air above it, the smoke stops rising and simply drifts off, but only at that level, which then traps the pollution close to the ground, and then everyone has to breathe it. So it essentially holds in more pollution as opposed to getting it up and out. Now, moving on to acid deposition. This occurs when sulfur dioxide and nitrogen monoxide combine with water in the air to form sulfuric acid and nitric acid. That falls to the earth later, wherever the wind has blown it. When rain washes the sulfuric and nitric acid out of the air, that's called wet deposition, because the acids are droplets in the air that have now been deposited on the earth. Another product of these two gases react in the air is solid particles of sulfate salts and nitrate salts, which are called dry deposition, when they settle out of the air and onto the ground. They're not acid directly, but it's like one of those cheap toys. Look, kids, it's sulfuric acid. Just add water and create your own acid rain. That's because when sulfate salts react with water on the ground, they form sulfuric acid, just like sulfuric acid did in the air. And there are many effects of acid deposition. It can damage any structures made of stone or metal, like buildings, cars, and statues. A hidden effect of low pH is that it can cause water to leach toxic metals from the soil into lakes and rivers used by people for drinking water and fishing. It can harm plants by damaging their leaves and reducing their photosynthesis, and by making the soil more acidic. Plants require a proper range of soil pH to grow properly, which is why farmers spend boatloads adding pulverized limestone or lime to the fields. Lime neutralizes acid, so adding it to the soil raises the pH to something more neutral, but it's not quite possible to add lime to everywhere in the world that's affected by acid rain. Last up is the increased acidity or lower pH caused by acid deposition can lower the pH of bodies of water, making it impossible for fish to survive. This lake looks really pretty, but the water's only clear because there's absolutely nothing living in this lake, and if you look at the shore, you'll see why. There was once a forest along the banks, but it's been killed by acid rain, and the acid washed into the lake, killed the plants and the fish, leaving the scene which now looks more like a cemetery than a pretty place to go fishing. Acid deposition is a real problem, and reducing its effect after they've happened can be done, but at great economic cost. Better ways to reduce its effects are to prevent acid deposition in the first place. Most of the sulfur that gets released into the air comes from burning sulfur-contained coal, like this train full of its way to a power plant. Unfortunately, coal that is naturally low in sulfur is more expensive, and cleaning coal to remove the sulfur costs money, as does adding scrubbers to smokestacks to remove some of the sulfur before it's released into the air. Now, let's move on to indoor air pollution, which has been ranked as the #1 air pollution problem for poor people in the world. You might be thinking, hold on, Mr. Peterson, air pollution is outside. My house is clean inside. I can just shut my doors and windows and avoid all of this. Well, you'd be very wrong. Now, you might think this one applies to you, but if you ever burn wood in a fireplace, you could be creating indoor air pollution nearly as bad as this woman is doing by cooking over a wood fire inside. In the Let's Be Thankful We Live in the First World Country department, this is the kitchen of the house. It's probably also the living room and the bedroom. Cooking with wood inside the home is terrible, because everyone in the house is breathing the smoke, which contains fine particles, along with the witch's brew of chemical pollutants, and everyone in the house is exposed to it multiple times per day. Then you have dust mite droppings that are a literal #2 on the list, and they are pretty bad for indoor air pollution as well, because these little guys live in your carpet, furniture, the mattress, on your bed. Oh man, they love your pillow. Your pillow is like the all-you-can-eat buffet around 12:30, 1 o'clock on Sundays, because dust mites eat dead skin, flakes, and oils. This guy isn't eating his Wheaties, he's eating a flake of dead skin. To him, it's a gigantic potato chip. He can't eat just one. Now, the droppings they leave behind trigger all kinds of allergic responses and asthma in humans, so that's another component of indoor air pollution. Just a parting thought. It is widely believed, although more scientific studies need to happen to prove it, conclusively, that your pillow will actually gain weight over years of use as the amount of dust mite droppings inside of it increases. I hope you sleep good tonight. Carpets are one of the dirtiest things in your home, but we don't clean them very often. That means they contain traces of everything you've tracked across them, whether it's pesticides that were sprayed in your lawn, chemicals you were working with in the garage, or pollutants you contaminated yourself with at work. They all get brought home, deposited on the carpet, and then over time they're released into the air for you to breathe. And then we have cockroach droppings. Are pretty awful too, because they trigger asthma and allergies as well. This is a picture from inside a cabinet, and the droppings look like dirt, but they're not. They are far, far worse. Then you got mold and mildew. Like these black mildew spots growing along the windowsill also cause indoor air pollution problems. Molds and mildews reproduce with spores, which float through the air to find new places to grow. They land all over the house, and anywhere that's slightly damp is a good place for them to grow. Along the way, we breathe some of them in and trigger allergies and asthma, just like cockroach and dust mites. This is visible mold, but mold can be growing undetected inside the walls and under your house if you have a crawl space, all the time damaging the structure of your home and making you sick without you being able to even tell. Why? And smoking indoors is another factor for indoor air pollution. We call it secondhand smoke because the smoke moves around the house, around the inside of the house, and some of the health effects of secondhand smoke are actually worse than smoking in the first place. And by the way, cars qualify for indoor air pollution as well, because as you drive down the road, your car can concentrate the exhaust fumes of other cars, making the air inside your car dirtier than the outside. Then you have formaldehyde, like the greenish-yellow liquid that this human brain is stored in to preserve it. It is another problem for indoor air pollution. Formaldehyde is added to the building materials, furniture, carpet, and even some clothing. It's left over in these products as a remnant from producing it. But as it sits in your house, it slowly releases the formaldehyde that's left into the air. And let's move on to radon. Radon is another problem for indoor air pollution, because many areas of the world contain natural uranium deposits underground. And as the uranium decays naturally, it produces another element called radium. And when that breaks down, one byproduct is called radon gas. It's colorless, odorless, and yes, it's radioactive. As it is produced, it seeps upward and finds its way into the air. That's not a big problem in the outside air because natural processes break it down over time and the wind takes it away. But if your house sits over the top of an area that is actually producing radon, it can seep into your house through cracks and your foundation and be trapped inside. So it can build up into harmful levels, because now you're breathing radioactive gas deep in your lungs. And what actually happens is it clings onto dust that you create, and then you breathe it in. And the radon gas is a carcinogen because it is commonly associated with increased risk of lung cancer. There are cheap test kits available to test your home for radon if you're interested. Now, lots of these indoor air pollution problems are more recent developments that didn't happen to some degree even several decades ago, as modern construction techniques have improved and buildings have become more and more insulated with a focus on less air leaking in and out of the house to save energy. What I call the law of unintended consequences raised its ugly head and brought about something called sick building syndrome. It occurs when people in a building exhibit symptoms of being sick, like coughing, headaches, nausea, fatigue, dry skin, and respiratory infections. It can occur because of high concentration of indoor air pollutants in a home or workplace. It's become more of a problem as buildings become more tightly sealed, because there's less fresh air coming into the building. And if you remember the saying, dilution is quite often the solution to most forms of pollution. There's real truth there. As we rely on air conditioners more, we open the windows less often. More modern construction is starting to feature air exchangers, which are devices that swap inside air for outside air. But as the air inside leaves, it's used to cool the warmer air that's entering, so that you don't lose much energy, but you get fresh air in. It works in the winter too, but it keeps the heat in while allowing fresh air to enter. Now, I'm sorry about this, but when I saw this picture, I had to include it. Now remember, on the AP exam in May, we'll see which of you really knows your stuff. Air pollution has many effects on your health, and I've already mentioned a few, like triggering allergy attacks, asthma, long-term exposure to some forms that can cause lung cancer. The sick building syndrome is usually an acute and usually dissipates after leaving the building, and the consequences usually become better very quickly. And these pollutions can also just lead to respiratory distress. Your respiratory system is designed to do just one thing: bring oxygen in and remove carbon dioxide from your body. That's it. To protect itself, it has several lines of defense. When you breathe in large particulates like dust, dirt, and smoke, many of them can get caught in your nasal passage. Hairs, the mucus in your nose, creates an effort to trap those particles and then wash them out by making your nose run, or getting them expelled when you sneeze. And the entire lining of your respiratory system is covered in microscopic cilia, like the lining of your throat and bronchial passages. As pollutants find their way deeper into your respiratory system, they land on the cilia, which wave back and forth like trees in the wind. But they rhythmically carry those pollutants back up your throat to the point where you can either swallow them, gross, or hack them up as phlegm. Those globular cells below the cilia are responsible for creating more mucus, which helps trap particles and remove them. The long and short of it is that breathing in air pollution can create respiratory problems, but it can also allow pollutants to be absorbed deep into your body, which can cause severe problems like heart attacks, strokes, and some forms of cancer. And if you're a smoker, smoke actually kills the cilia, which allows more respiratory problems to occur. In the U.S., it is estimated that 250,000 people die annually from causes related to air pollution. That's a lot of people. So what do we do about it? Laws and regulations are one way, and they've made great strides in cleaning up air pollution in many areas of the world. Air pollution is a relatively likable environmental cleanup task because everyone can see its effects, and nobody likes to see grandma hooked up to her oxygen tank because of her emphysema. So, more people are willing to do something about air pollution than some other forms of pollution that are less widespread or harder to see. The U.S. passage of the Clean Air Act led to reductions of many air pollutants by establishing air pollution regulations for states and cities. Air quality has actually increased in many areas because of these regulations, including the federal ban on leaded gasoline in 1976. More laws can be passed in the future, and we'll likely see that occur to address new problems of air pollution as they come up. There are ways to improve, though. Pollution cleanup or fixing it after the fact is a costly strategy because it's harder to clean up the effects of air pollution than it is to prevent it in the first place. When I was your age, if you took your car to the shop to have the air conditioner repaired, then oftentimes all the refrigerant that cools the air would be released into the air and replaced with new refrigerant when the job was done. The refrigerant, called Freon, was what it is known as CFCs, or Chlorofluorocarbons, which is a chemical that drifts up to the stratosphere, and it's like Pac-Man. And ozone molecules are the pellets. It will destroy the ozone, and is still destroying it today. So, in the Global Environmental Success Story Department, you can chalk up the story of the ozone hole because, by and large, the world has come around on that one to understand that the ozone layer is pretty important. So, most countries ban the use of CFCs because there's no way to fix the damage we created except to let nature create more ozone. It's going to take decades for that to occur, but new damage has been slowed by adopting CFC-free refrigerants and older equipment that still contain Freon is serviced with machinery that can remove the Freon and store it without releasing it into the air. It's just easier and cheaper to prevent air pollution than it is to clean it up. Another way to improve our situation is to make less pollution by increasing the average fuel economy of our motor vehicles. This is something that is set by law, but increasing the average fuel economy of vehicles, especially vehicles like trucks and SUVs that are currently exempt from these standards, would go a long way to reducing air pollution, and they are actually making this better and better as we speak. Adding to the trouble is that there is very little federal regulation of these kinds of engines that power lawnmowers, generators, and lots of other equipment. For every gallon of gas these burn, they release 50 to 100 times as much air pollution as average car engines. And then there's the problem of sources of pollution that fall outside the scope of modern law. Ever wonder why so many cruise ships and cargo ships fly under the flag of some obscure nation? One reason is because those countries have much weaker pollution control laws. So it's cheaper to fly the flag of that country while moving around the world in countries that have stricter pollution regulations because the laws don't apply to them. That could be changed, but that's the way it is now. Plus, what country has legal authority over international waters? Yep, nobody. And that's a tragedy of the commons. Another way to improve is to focus on global emissions of CO2. It's often ignored, but it's becoming more of a problem with global climate change, which we'll get into in a later unit. Now it's not all doom and gloom. There are many ways to reduce air pollution, and I'll ask you to be sure to read these in your book. You don't need to know every single one of them, but know some examples from a variety of different strategies. There's the idea of increasing energy efficiency so that less coal needs to be burned to generate electricity, and therefore reducing air pollution by using more renewable sources of energy. There are several ways to modernize buildings to reduce indoor air pollution, like limiting formaldehyde, use and production of materials, banning indoor smoking, and using green design principles to incorporate fresh air into a building without reducing the comfort provided by air conditioning. So just go check out the book for a little more information on this. Now, to move on to the last section of the notes, we need to talk a bit about the ozone layer. Ozone in the lower atmosphere is an air pollutant, but in the stratosphere it's needed to shield us from most of the UV radiation of the sun. Without it, we'd suffer from more sunburns, cataracts, increased acid rain, more skin cancer, and decreased photosynthesis. Ozone depletion first started being noticed in the 1980s when measurements revealed that the ozone concentration of the atmosphere was dropping. At the same time, it was noticed that every October and November, a pretty large hole in the ozone layer was opening up over Antarctica. In this picture, the purple and blue sections show low ozone concentration areas, and so it got nicknamed the ozone hole. It varies from year to year in shape and size, but it's there. A smaller hole was discovered over the Arctic in the spring, and people got very concerned, very fast, because it was well known at the time that ozone was needed for. The culprit turned out to be a class of molecules called chlorofluorocarbons, or CFCs, which was mentioned in another podcast. Their trade name was Freon. They were used as coolants for air conditioners and refrigerators, and they were propellants in almost every spray can. And they were useful for cleaning delicate computer parts because they didn't react with anything. They were non-toxic, non-flammable, and they were cheap. That means we used a whole bunch of them. As it turned out, the CFCs were released into the atmosphere. They broke down to release chlorine atoms when UV radiation hit them. Then that chlorine then joins with ozone molecules and removes an oxygen, leaving regular O2 gas. The process continues, and one atom of chlorine can destroy thousands of molecules of ozone before it's removed from the air. Now, I've already mentioned a few effects of the ozone loss and a few other surprising ones, including these effects. UV radiation can increase smog production, and it can degrade outdoor paints and plastics. If you've ever seen how plastic left outside in the sun becomes faded and brittle, that's due to the effects of UV radiation. And the good news is that the ozone loss is being reversed. In 1987, an international agreement between 36 countries was made to stop the emissions of CFCs into the atmosphere, and those chemicals have been phased out and replaced by less damaging chemicals. People still call this stuff you put into a refrigerant Freon, but it's a completely different chemical these days. Since the agreement back in 1987, emissions of CFCs have been reduced all over the world, and the ozone hole, while not fixed completely, is stabilizing and showing signs that it will recover fully over the next few decades. It's a great environmental success story where government, industries, and the general public agreed that something had to be done, regardless of the cost, because the alternatives were too costly to even consider. It's my great hope for the future that this story gets repeated with every major environmental concern, because I think we have it in us to fix any problem that confronts us. We just have to want to do it. And that's it for this screencast. Thanks for watching.